In this lesson, we will solve a very famous programming interview question. And the question is that given a sorted list of integers, we want to find out how many times a particular element occurs in this list. So let's say we are given a list in the form of an array. Here we have an array of size 12 and the elements are in increasing order. Now, how many times does number 5 occur in this array? 5 occurs 5 times. And how many times does number 2 occur in this array? 2 does not occur in the array. So we will be given any such sorted array A and a number x, and we have to find out how many times this number x exists in this array A. Now we want to solve this problem programmatically. So let us think through the different approaches that we may want to follow. The simplest approach is that we can scan the whole array and count the occurrences of x in the array. So if I have to write a function find count that will take as argument the array A, its size n, and the element x to be searched for, the element x for which we want to find out the count. So the logic would be pretty straightforward. We will take a variable initially, let's say the name of the variable is count, and we initialize it to 0, and then we run a loop starting 0 till n minus 1, and if ai, or the element at index I, is equal to the element x, we increment count, so count becomes count plus 1, and finally when we come out of this loop, we return count. So we are performing a linear search where we are scanning the whole array to search for element x. We could optimize this algorithm a little bit, something like this. Because the array is sorted, once we reach a stage when ai becomes greater than x, we can stop counting. But still, in the worst case, this loop will run n times. When all the elements in the array are same, then this loop will run n times. So in the worst case, this algorithm, the running time of this algorithm is proportional to n. In other words, the time complexity is big O of n. This is a very simple solution for this problem, and if you give this solution in a programming interview, the interviewer would be like, I do not like this, give me something better. So how do we find out a better solution? Whenever in a problem we are given a sorted data or a sorted collection, we should try to think about applying one very famous algorithm that makes the best use of this property that the data is sorted, and this algorithm is binary search. So can we make use of binary search in this problem? One thing that we can do is that using binary search, we can find out any occurrence of the number x in the array. So let's say in this example we want to find out count of number 5. So let's say we find out using binary search in big O of log n time that number 5 exists at index 6. Now because the array is sorted, all occurrences of 5 will be adjacent to this. So we can go towards higher indices starting this index and look for all the 5, and then we can go towards the lower indices and look for all occurrences of 5. But once again, if the whole array is number 5 only, all elements being same, still is a sorted array, then we will scan all the elements, we will access all the elements in the array, and eventually the time complexity will be big O of n only. The time taken will be proportional to n only in the worst case. So using binary search kind of does not give us much advantage if we use binary search in its basic form. Big O of n, because to perform binary search we will take big O of log n time, and then to find out all the adjacent occurrences of x, we will take big O of n in the worst case. So for higher values of n, log n is negligible in comparison to n, so this is eventually big O of n. We are not writing pseudocode for this approach. We leave that as an exercise for you. With these two approaches, we are still big O of n in the worst case. So what do we do? Well, if you remember from our previous lessons on binary search, we can write a binary search to find out the first occurrence of an element in an array. And similarly, we can write a variation of binary search to find out the last occurrence of an element in an array. And this forms the basis of our third approach. And I'll clear some of this and make some space. Okay, so we can use one variant of binary search to find out the first occurrence of an element in the array, and we can use another variation of binary search to find out the last occurrence. And if we know the last and the first index at which the element occurs, then we also know the count of it in the array. So once again we will write a method find count that will take an array A, its size n, and the element x, and let's say we find the first occurrence of the element in the array using a method find first, which is a variation of binary search, and we will use another method call to another variant of binary search that will give us the last occurrence of the element in the array. Then we can return count as last index minus first index plus 1, and I'm not handling the case here when the element is not present in the array. Let's say we will handle it well in our actual implementation. Okay, so the first method call, if we are using binary search, will work in big O of log n, and the second method call to find out the last occurrence will also work in big O of log n. So overall, the time complexity to find out the count of an element in the array would be big O of log n. And that's really great. We have described how to find out the first or last occurrence of an element in a sorted array using binary search. We had written pseudocode for the algorithm in our previous lesson, and there is a link to the previous lesson in the description of this lesson. But let us now go and write some real code to solve this problem. I will write a C program. Let us first write a simple normal binary search, and then we will modify it to find the first or the last occurrence. Let's say we have a method binary search that gives me the index of element x in the array. In binary search, we first define two indices, low and high, two variables low and high initially set to 0 and n minus 1 respectively. And then we find the mid element as low plus the mid index as low plus high upon 2. And then we compare the middle element with the number x, and if middle element is equal to x, we have found our element, so we simply return the index mid. Else, if x is less than the middle element, because the array is sorted, remember array being sorted is a precondition of binary search, we set high as mid minus 1, kind of saying that search in the segment left to the middle element. And if x is greater than the middle element, we adjust low to mid plus 1. And we keep repeating this process again and again till the time we have a valid segment, and a valid segment is till the time low is less than or equal to high. And if we come out of this loop without finding anything, then we return minus 1 to say that x does not exist in the array. Problem with this implementation is that as soon as we find any x, we return. So there is no guarantee that we will find the first index or the last index if there are duplicates of x in the array. So what we will do is we will modify the algorithm slightly. We will have another variable, initialize it to minus 1, and now when we find x, then we do not return an exit. We update the result variable to kind of say that okay, this is the lowest index of x so far, and then we continue the search. So if we want to find out the first occurrence, then we adjust high to mid minus 1. So we update result and go on searching towards lower indices, lower segment, and finally when we come out of this loop, then we return result. So if we do not find anything, any occurrence of x, we simply return minus 1 because this was initialized to minus 1. Now this implementation will give us the first occurrence of x in the array. And what if we wanted the last occurrence? The only difference would be that we will go on searching towards right or higher indices. So we will say that low is equal to mid plus 1. Now go on searching towards the higher indices. Now I want two different functions for finding out the first or the last occurrence. But if you see, there is difference in only one line in these two implementations. So what I'll do is I'll use the same function to retrieve both first and the last index based upon another argument, a flag. So let's say we have a flag as a Boolean parameter, search first, If it is true, we want to search for the first occurrence, and if it is false, then we want to search for the last occurrence. So if we want to search for the first occurrence, then we want to, in the case when a mid is equal to x, we want to adjust high to mid minus 1, else we want to adjust low to mid plus 1. Okay, let us now write the main method. What I'll do is I'll first initialize an array, and I'll ask the user to input a number x. Now we want to find out the count of x, so we will first make a call to binary search method to find out the first index in the array. So we will pass the array A, the number of elements in the array, which is 12, and we may also calculate the number of elements using this particular equation, size of A upon size of A0, size of the number of bytes in the whole array upon the number of bytes in each integer, in each element. And we want to search for x, and we will pass true, because in our method declaration, if this flag is passed as true, then we search for the first index, else we search for the last index. Now if first index is returned as -1, then the element is not in the array, so no need to find the last index. We can simply print that the count is 0, else we find out the last index, and this time we make the call to the same function, binary search, with the only difference that this time we will pass the flag as false. So we will say that, hey, give me the last index, and we will print count as last index minus first index plus 1. So this is our code, this is our method binary search, and we have made call to binary search twice to find out the first and the last index, and we decide first or last index using this flag. Let us now run this code and see what happens. Let's say we want to find out the count of number 3. Then this gives us that 3 occurs twice, which is right. Let's now try number 5, and count of 5 is 5, and let's give x is equal to 2. 2 is not present in the array, so the count will be 0. So this is an optimized algorithm to find out count of an element in a sorted array. This is a classic implementation of binary search. In the coming lessons we will see more problems on binary search. So thanks for watching.